Quantum numbers. So these are going to be the ways in which we're going to use these to describe where an electron is around an atom or within an atom, around the nucleus. And essentially this is kind of like the address of the electrons itself, and this allows us to understand the quantum model of the atom itself. So Bohr's planetary model could only explain general energy levels of the electrons, and there's more detail about what's going on with those electrons around the nucleus than just saying it's on the first orbital or the second orbital or so on. And so we need more than just one descriptor for an electron's position than what the Bohr model would allow us. However, one of these bits of information is quite similar to what Bohr provided to us with the orbital. And this is the first of 4 pieces of information about an electron's position. So instead of just saying an electron's on the first orbital, and that's all we need to know for Bohr model, what we're going to be doing now is instead of just saying one thing, we're going to say 4 things. This is the first of those 4 things, and the first one is pretty similar to the orbitals that Bohr used. So we're going to call this the principal quantum number, and each of the 4 bits of information have a particular symbol we use to represent them, so we don't have to write out the name each time. And so the principal quantum number, this is the first bit of information we need to know about where an electron is, and it is going to have a small n to denote when we're talking about it. When you solve the wave equation, so Schrödinger's wave equation for the position of, or the possible positions of these electrons around the nucleus, there's certain values that can be used for these bits of information that we're going to be using just to describe where the electron is. So first part of those bits is the principal quantum number, and it can only be whole number integers. And so if you're looking at the principal quantum number for any electron around any atom, it's going to have one of these whole value integers. So this principal quantum number could be 1, could be 2, could be 3, could be 4. So far it's pretty similar to the Bohr-Rutherford model. You could think of this as being like with the orbital where the electron is found. And so we're going to call this the shell. And we'll use some of this terminology as we go through it, but think of this as the energy level that the electron has, the shell that it is on. And so if n equals 1, it's on the first energy level, and that's the lowest one. The ground configuration is always going to try to be the lowest. So if there's only one electron and it's in this ground configuration, it'll be on the first shell, or the lowest energy level. So n would equal 1. However, if you have more electrons, or the electrons have more energy, they could be higher up. So n could equal 2 or 3 or 4 or any whole value. Again, you can think of these as being similar to the orbitals you'd see in a Bohr-Rutherford model, but realize we're going beyond that, because if you say that, I don't know, an electron's on the second orbital, that gives you some information, but there's more information needed. So this is the first of 4 bits of information. This is the principal quantum number. One thing we should note is that as the energy levels increase, so as we go from n equals 1 up higher to n equals 2, the difference between them, so the difference between 1 and 2 is greater than 2 and 3, and that's greater than the difference between 3 and 4. So as the electrons get higher energy, the difference between those energy levels becomes less, and this is going to help us explain some of the overlap that we see later on. So that's the first bit of information, the principal quantum number, similar to Bohr's Rutherford model, and sort of tells you the energy the electron has. However, there was more to an electron than just that it was on a particular shell. So additional spectral lines can be seen when you actually look at the emission spectrum of atoms, and they say that, okay, if you're on, let's say, shell number 2, you could have 2 different electrons both on shell number 2, but they have different energy levels. So there's something different about those electrons that needs to be accounted for. So essentially, there is the introduction of these subshells. So you can think of them as being little energy levels within a particular energy level. So subshells within a shell. This is the second bit of information that we're going to be describing about an electron's position. So the first one is which shell it's on, and then the second one is which subshell it is on. And what this is just briefly describing it, the secondary angular quantum number. It has its own little symbol, and this is like a lowercase italicized L. This gives us the shape of the electron orbit, and we'll see some pictures of this. But think of these subshells as having different shapes to them, and so depending on which shell you're on, you could be on, say, shell number 2, and you could have shape A or shape B. So this will tell us which shape we happen to have, and we'll use other letters than that. Think of these as little steps within each energy shell. The possible values for these are based on what n is. So there's limitations as to which values we could have. You could have an L value, and we're going to use these as labels. So the L value itself could have a value of 0. So we're going to think of that, again, this is referring to the shape. So think of that as a label. It's not saying it's nothing. It's saying that it has the shape, and we're going to call that shape 0. And this shape could go up to the options possible, whatever n is minus 1. So for example, if you're on shell 1, if principal quantum number is equal to 1, then the only possibility for the shape, or the secondary quantum number, would be an L value of 0, because that goes from 0 up to 1 minus 1, which is 0. And so the only possibilities are shapes 0, or secondary quantum numbers 0. If, though, you're on the second shell, then principal quantum number is 2, then your L values could be from 0 up to n minus 1, so 2 minus 1, which equals 1. And so you could have 0, or you could have option 1. And again, don't think of these as having a particular value that's important to us. We think of these as being 2 different options. So you could have shape 0, or you could have shape number 1. And then, of course, the higher the n value is, the more possible shapes there are on those shells. So to make things a little bit easier later, once we've done some labeling with this, we're going to take our L values and we're going to turn them, the numbers that give us the possibilities, the 0 to n minus 1, because remember the L values are from 0, n of whatever your n value is, 0 up to n minus 1, so our n values could be 1 or 2 or 3. Whatever those are, they'll have possible L values. And to make the labeling easier, we're going to turn these, and it doesn't seem easier right now, but it will be. We're going to tell these L values, turn these L values, numbers, into letters. So if we said, as we previously did, maybe the option for a subshell could be 0, we're going to call that S. And if the option for an L value is 1, we're going to refer to that as P. And these have names to them that we don't really need to worry about. But 0 is going to be called S, 1 is going to be called P, 2 is going to be called D, and 3 is going to be called F. We're not going to be using these very commonly, anything past F even, because that'll cover all of the electron placements within the periodic table. So if you had to, it goes alphabetical after that. But really, the main ones we're going to be using for a lot of the bonding we're doing, because we don't get too big in terms of our elements, are going to be SPs or Ds, and then occasionally we'll see some Fs. Each letter has a specific shape. So remember that we had our S shape, which was an L value of 0, which we're now going to call, so if L equals 0, we're going to call that S now. If L equals 1, we're going to translate that to be a P. And if L equals 2, we're going to translate that to be a D. And if we had an L value of 3, we're going to translate that to be an F. But again, we don't really see those Fs very commonly. But when we say that this principal quantum number denotes the shape of the electron, and it's not really the electron itself, it's more the three-dimensional probability area where you might find the electron. This, look at more quantum mechanics stuff if you want regarding that, but this is what we're going to be using to denote the shape of the space where the electron could be found. Again, most commonly we'll be talking S, P, or D. And what you can see with this, and we'll look at how you get this calculation here, but what you can see is depending on which shape you're dealing with, so what the secondary quantum number is, there's different options. So if you are shape S, there's only one type of shape S. But shape P, there's actually these 3 types. And so that's actually the next part that we need to get figured out. So the Zeeman effect is when the spectral lines split within a magnetic field. And this told us that there's another property of these electrons, not just the shell and the subshell, the energy level and the shape, but there's something else about these electrons that's being affected by a magnetic field. And so what this came to be called, this gave us our third quantum number. This is the magnetic quantum number. And essentially, this is the orientation of the shape. So there's a shell and a subshell, and then there are orientations of those subshells. And they are dependent on, so the ML is the symbol we're going to be using for the third quantum number, the magnetic quantum number. And again, think of this as the orientation. Its values are based on which shape you have. So depending on which L value you have, there's possible different ML values. So for example, if your L value was 0, remember L is based on your N value, so if your L value happens to be 0, then the only possible ML value would be 0, because minus 0 plus 0 and 0 are the same thing. However, let's say your L value was 1, then using this formula here for calculating what the possible orientations could be for that particular shape, so a shape of L equals 1. And again, don't think of 1 as a quantity, think of it as a label. So if that L is 1, then your ML value could be minus 1, 0, or positive 1. And then the higher the L values, the more possible orientations you could have. Then, that's 3 of the bits of information we have about electrons so far. The final bit of information was that upon closer inspection, the spectral lines are actually found in pairs. So there's one last aspect of an electron that needed to be included in order to be able to describe its placement around the nucleus. So this gives us our fourth quantum number, and this unfortunately is called spin, because as soon as you see the word spin, you think, okay, that must be what the electron is doing, is spinning. Watch full videos about what that actually means. Probably a better way to think of it, as Pauly described it, is this is an aspect of the electron, and you can call it classically non-describable two-valuedness. And so it's referred to as the spin. There are two possibilities. If you want to think of it as clockwise and counterclockwise, that's fine, but not correct. But it is some aspect of the electron itself of which there are two possibilities. So the spin quantum number, the classically non-describable two-valuedness of each electron, or it has two possibilities of these, is that it could be either, and we have the calculation for this, it's given the symbol ms, and it can either be a positive 1/2 or a negative 1/2. And again, what those numbers actually means, not important, we're not doing the math on it, but the point is it can be either one or the other. And again, if you want to make it simple, you could think clockwise, counterclockwise, or that's not correct, as it's not like the electrons themselves are actually spinning, but what it is that there is some aspect about these electrons of which it could be either one or the other. So essentially this is going to be giving us the last bit of information about the electrons around the nucleus. So, to summarize, we have not just one bit of information saying where the electron is, like with the Bohr-Rutherford model, you can just say, oh, it's on orbit 1 or orbit 2 or orbit 3, and that's all you need to know. What the quantum model gives us is that there's actually 4 bits of information. If you want to say where an electron is, you've got to give it 4 bits of information. It's kind of like an address. You can't just say, oh, I live at 50. That doesn't work for an address, because that could be your house number, but without the street and the province, or the city and the province, then it doesn't really give you enough information to actually place the electron. So we need these 4 bits of information. The first one is the principal quantum number, and so this gives us, this is again symbol n. Think of this as the energy level. The possible values are all whole number integers. Then the subshell. This is given the symbol italicized lowercase l, and think of this as being the shape. The possibilities for that shape are based on which shell you're on, and so depending on your n value, you're going to have certain l values. Then each of these shapes has a particular orientation, or certain amounts of orientations, and so the higher the L value is, the more possible orientations you can have. And again, we have our calculation for finding out the L value, we have our calculation for finding out the ML value, and then finally for each one of these possibilities, every single ML value you have will have one of 2 possible MS values, or spin values, and it can either be positive 1/2 or negative 1/2. And that it's 1/2 doesn't matter for what we're doing. You can think of it as being like up and down. That would be just as descriptive for this classically non-describable two-valuedness that these electrons have. So each orientation has 2 spins. We're going our way backwards here. So electrons can be found in these shapes which have particular orientations. Every single orientation has one of 2 spins. The orientations are defined by the shapes. So depending on which shape you have, there's more or fewer possible orientations. Again, each orientation has 2 spins. And the shapes themselves are defined by the energy level. So we have an electron that's on a particular energy level. While it's on that energy level, it's going to be existing in a particular shape. Those shapes have certain orientations, and for every single orientation there are 2 possible spins. So these are the 4 bits of information we need to describe the placement of an electron around a nucleus. That being said, we can start putting it all together. So to start off, we can say, okay, we have these 4 bits of information. We have our N, we have our L, we have our ML, or our orientation, and then let's go our M, our spin die. So of the possible values for our principal quantum number N, we could have, let's say, principal quantum number 1, or we could have principal quantum number 2, or we could have principal quantum number 3, whole number integers. We could also have 4 over here. As you can imagine, as the numbers get higher, the possible values are going to be increasing as well. So you can have a lot more options for higher N values. Now, based on what our L is, L can be from N up to, oh, that's not correct. Let me erase that here. So L can equal 0 up to N minus 1. So if, let me get some more room here. Write that underneath. From 0 to N minus 1, those are the rules that dictate what L could be. So if N happened to be 1, then L can only be 0. That's the only possibility that L can be. Then based on that, so again, what that means is at principal quantum number 1, the possible shapes are only shape 0. And remember, we call shape 0 shape S to help with the labeling later on. But if you are in shape 0, then your ML values are from, the possible ones allowed are from minus L up through 0 to positive L, including 0. So what that means is if your L value is 0, then that only gives you one possible ML value of 0. Then, so again, our principal quantum number is 1, and then our shape is 0, which we'll call shape S, and then the orientations, the possible number of orientations for shape S are only ML value of 0, which, see, think of that as being only one possible orientation. But within that possible orientation, we have 2 spin values, and it could be negative 1/2 or it could be positive 1/2. So those are both possible orientations for this particular quantum tree. So we can think of this, and the reason why it's called a quantum tree is because you look at what the values are, and then from there you're going to have possible options. So under principal quantum number 1, then there is only one possible shape, shape 0 or S, which can only have one possible orientation, but within that orientation there are actually 2 possible nondescript 2-valuednesses for those electrons themselves. Now let's try this out for principal quantum number 2. So that is the principal quantum number. Think of that as being the shell number or the energy level. Its L values, though, can be from 0 to 1 because both of those are allowed using the rules for determining the L values from 0 up to N minus 1, and since N is 2, we can have either 0 or 1. And think of these as being options. These are like possible addresses for the electrons. So if you want to think of these as addresses, we could think of this as the n value is like the most general term, which would have the most things within it. This is kind of like a province. And then the L value is kind of like a city. And then the ML value is kind of like a street name. And then the magnetic spin would be like house numbers. Every street in this particular world only has 2 houses in it, 2 options. But if you look at this other province n equals 2, then there are actually 2 cities here. And those are the possible n values. The ML values for shape 0, again, are only 0. So this particular option only has, this particular shape only has 1 orientation. But this orientation, as with the previous one, also has 2 possible spin numbers. And so it could be either -1/2 or +1/2. Now it's a little bit more interesting when we get to the ML value for principal quantum number 2. The L value could be 0 or it could be 1. If it was 1, then the NL values go from, oh, that's not blue, from -1 or 0 or +1. So there's 3 options for this new shape. Let's get some yellow in here. This shape L here. It could have a, so again, remember this is the shape L, and we're going to call that P later on. And so shape L could have a -1 orientation. Don't think of them as values, think of them as labels. A 0 orientation, or a +1 orientation. There are 3 ways of orienting shape L. Now, for each of those orientations, there will be 2 possible undescribable 2-valuedness, also known as spin, -1/2, +1/2, -1/2, and this is getting messy up here. Don't quite line up, but you can get the point, hopefully. This shape L could be an orientation -1, and if it were, it could have 2 possible spin values. If the shape L were in orientation 0, then it could have 2 possible spin values. If shape L were in orientation +1, then it could have 2 possible spin values as well. So this is a quantum tree, and you can start seeing why it looks like a tree. It is the layout of the possible values based on the Schrödinger-Wave equation for the location of the electrons. And let's try going through our L values for principal quantum number 3. So again, it could go from 0 to, or it could be 1, or it could be 2. And so if your principal quantum number is 3, you could have shape 0, shape 1, or shape 2. And it's going to get crazy messy here, but you'd imagine for shape 0, it could have an ML value of 0. That's the only possible orientation for the shape 0, just as it has always been. And that one is going to also have, I'm going to run out of room here for sure, -1/2 and +1/2. Landscape's better for doing this. And so that, again, principal quantum number 3 has 3 possible shapes. For shape 0, there's only 1 possible orientation. For that particular orientation, there are 2 possible spins. And to repeat ourselves again, if you are in shape 1, then your possible orientations are -1, 0, or +1. And again, those 3 are all options for shape 1, also known as shape P. And then for every single one of those, to the lines first because I'm going to run out of room, there are 2 possible orientations. Scribble this in here and you pretend like you know what it says. So every single one of those orientations has 2 possible spin values. 1, 2, 3, 4, 5, 6. Good. And then for shape 2, it is going to have even more options. Again, I'm running out of room here, but you can imagine for the ML values, it would go from -2 to -1 to 0, and off screen +1 and +2, and then each one of those orientations would have 2 spin values as well. So the point is that you would actually have 5 possible orientations for shape 2. Now, and again, you can imagine these would each have 2 spin values for each of those orientations. So quick summary before we go any further. Again, think of the rules for quantum numbers give you, it's like an address for the electron. Every single electron is going to have one bit of information for each of these values. You're going to have a bit of information about which energy its level's on, which shape it has, which orientation it's in within that shape, and then which of the two possible valuednesses, undescribable valuednesses, the spins would it have within those. So it's kind of, again, it's like knowing an address where you have a province or state, a city, a street, and a house number, and all 4 bits of this information are necessary to know the location of that electron. And do notice that this city here and this city here have the same name, but they're not in the same province, right? And so it is going to be 2 different locations, and this is one of the rules with quantum numbers, is they can't have, there's no 2 electrons around the same atom that can have all 4 of the same values. Now, one little kink to this is, as we saw, as the energy levels get higher, the difference between them gets smaller. So something unfortunate that happens, but once you figure out how this relates to the periodic table, it's pretty easy to get over. Once you get to principal quantum number 4, it, as you know, the possible L values would be 0, 1, 2, and 3. However, it's shape 0. So if you're at principal quantum number 4, it has shape 0, 1, 2, and 3. Its shape 0 actually kind of buds in line here. So it's not going to follow in order perfectly. There's going to be some overlapping. Shape 2 from principal quantum number 3 happens to actually, once you get electrons in, it happens to actually be higher in energy than principal quantum numbers 4, shape 0. And so principal quantum numbers 4, shape 0 is actually at a lower energy. And of course, because it's shape 0, you know that it would have a ML value of 0. And then of course, that ML value would have 2 possible spins as well. So we actually have a little bit of an overlap here between these energy levels once they get electrons in them. And again, you don't have to memorize that happens. The periodic table will tell you that it happens once you can relate how these quantum numbers actually dictate the arrangement of the periodic table.